this started. Okay. Okay, welcome back. So before we continue to our lecture, so I just noticed there's one question posted in the team chat room there. So this is the questions. Okay. I'm still reading on these questions here. So what you're trying to ask. Okay, cool. So this is the questions. If AK is the open close interval 1 over K2, limit of Pn is 0 to limits of 1 over K equals to 0 is obvious, but if AK is what actually? What is this? Wow, what is this? Square of K, then multiple. Oh, okay, so this is the one. This is half. It's not obvious. Don't need to prove or exam, or will not be that hard. Okay. 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 To me, right? Whether you need to write down the steps or not, it's again based on your intuition. So you look at the thing whether you ask yourself whether that is obvious or not. So if you think that is obvious, so then you don't have to. You don't have to explain the step for it. So if you notice something that is not obvious, so maybe you can just spend your time to explain it. So for example, like this, when I just look at it, I'm not sure whether the limit is really half or not. Is it really half? Yeah, I think so. Yeah. Yes, it's half. But I think never mind. So I think in this case, maybe you can just write a few steps to explain it. Okay. Right. So I hope I have answered your questions.
Oh, yes. Okay.
Okay. Is that true? I think so. Okay. Yeah. Okay. So now, so let's come back to our lectures here. Yeah, I think this is where we stop. So this is what we have discussed just now. Just for your knowledge, okay. So that this is a fact. So you don't have to. I'm not going to ask you to prove it, and you don't have to prove it. So okay, that is when omega is R. So it is impossible to design a probability to which could assign each subset a value. So this is proven already. So the proof is, like I said, beyond the scope of this subject. So this is and belongs to advanced rate analysis. Okay, so if you are interested on the proof, so you may read these books, Royton's rate analysis. Okay, so which is under the topics of we call it a Lebesgue measure and so on. Okay. Okay, so we just accept this without proof. Okay, so that means when omega is R, we are not allowed to set the sigma field to be P omega. That means we cannot take any subset to be an event. So because of this, then we have to set criteria for events. Okay, so this is why we have design definition 1.1.1. Okay.
Is it possible to see a counter example of how we cannot assign a function to subset to get a real number?
Okay. Unfortunately, in mathematics, it's very common like that. Okay. Yes, there is a counter example. If you want to know that this is the one, you may read these books. Okay. However, if you want me to describe that counter example, so I might need to spend 1 hour to explain how to construct that. So that is actually not that obvious. Okay, it's sort of like we go through a series of sequence to do a constructions. Okay, so in fact, if you want to know, you may Google. You're going to see. I believe in YouTube, even in YouTube, you may able to see some video which demonstrate the constructions. Okay. Yeah. So maybe you can look at here. What you need to do is I running out of space. Where should I put? Okay. Maybe I can just put it over here. What you can do is maybe you can see, I believe you should able to look at YouTube. So non-measurable set. Non-measurable set. So I believe you should able to get some video. Okay, or you can read these books. But I can tell you, the construction is not that obvious. You have to go through a series of procedure. Okay. In fact, it's almost impossible for you to look at how the thing looks like. We can only know that it's some kind of constructions for that. Yeah. So if you're interested, you may look at it. So measure non-lab measurable, maybe to be more accurate. So see whether you can get it or not. Lab measurable. I believe you should be able to get it. Measurable set in YouTube. So hopefully you enjoy those video. You may look at this box. This is one of it. The Leuden box. You should be able to get the construction of that counter examples. Okay.
Okay, thank you.
No problem. I think if I really want to talk about the construction, it's more than 1 hour. We have to begin with some kind of lecture first. Okay. After discussion of several lecture, and then we can spend some time to talk about the construction. So okay, then forget about it. So just accept it. So if you want, you may go and Google it on yourself. Okay. In nowadays, you can always get the information from the internet on yourself. Okay, got it. All right. So that's the thing. Now we come up with conclusions. We cannot simply take any subset to be an event. So that's why we can only set particular types of subset to be event. To be event. So that's why we set a criteria for event. So that is this 1, 2, 3 over here. Yeah. So that's the case. First, I think we have discussed this already in our previous lecture. So just go through it once again. First of all, the sample space omega must be an event. Okay, next. The complement of an event must be event. Okay. The countable union of events, again, event. So it has to fulfill these 3 properties. If we have a class of subset which fulfill these 3 properties, then we can say it is a sigma field. Okay. Okay. Why we want to choose a sigma field which fulfill this criteria? So which is actually based on the behavior of a probability. Okay. So this 1, 2, 3. So we have already discussed why we want to set these 3 to be a criteria for probability. So that is actually based on our observations. A probability should have these 3 properties. Yeah. Okay. So P of omega is 1. Probability is always it cannot have negative probability. Okay. And if we have a disjoint event, okay, so the probability of union of this disjoint event must be the sum of them. So this is the criterion for probability measure. Okay. Okay, so let's go through it once again for here. Okay, so again, one more time, we have discussed this already. So the formulation, this is for the finite sample space. Okay, what we can do is we can just simply take F to be the power set. So I believe this one is proven already. Okay, we have discussed this already. Okay. So it's proven. This one done, right? So it's proven. this definitely this one must be a sigma field. Okay. Okay, next, we construct a probability function which fulfill these two criteria. And we just define our P to be this. Okay, now we have a questions. Okay, we have a questions. Is this a probability? Okay, is this a probability? In other words, we want to see, is this further satisfy the action in definition 1.1.2? Okay, so so before we proceed, we have to verify first, make sure it fulfill the three criteria in definition 1.1.2. That is here. Okay. Once we define this, we have to make sure, yeah, you have to fulfill these three properties here. 1, 2, 3. Okay. So this is the thing. Okay, never mind. We do it together with the case B. Okay, as I said, so the proof for P being a probability measure is postponed to note 1. Okay, so we do it together with the case B. Okay, all right. Okay, so we have discussed these examples already. Another example for the finite case we have discussed. Okay, so in fact, this example could be categorized as this, the uniform distributions. Okay. So in general, for finite sample space, so this is the standard way to construct the probability space. Okay. Again, we have discussed this already. Okay. Next, proceed to this. So this is for the infinite discrete case. Okay. Again, we have discussed this one already. So we can just simply take the sigma field to be the power set. So that means any subset will be a power set. So any subset will be an event. Okay. Again, we can define a probability function like this. And then we define our P to be this one. Okay, again, now we need to, okay, this one we have is proven. Power set must be a sigma field. Okay. Now we need to verify. Okay. We need to verify that P must fulfill the definition, the three actions in definition 1.1.2. Yeah. So we have to verify P fulfill definition 1.1.2. This one done already in our last lecture. That means we have to make sure our P fulfill these three properties here. Okay. Okay, let's do it one by one. Okay, I think this one we skip. Okay, look at it. Okay, we now show that P is a probability measure on F. That is, it satisfies actions in definitions 1.1.2. Okay, right. Based on this, I think it's clear that PA is greater or equal to 0 for all A. I think it's clear because of all the P omega K are non-negative. So then this must be non-negative. Next, P of omega is 1. So it's actually based on here. Okay, I think 2. Okay, the only thing will be number 3. Okay, this is, we can do it in this way. How should new page or what?
Sorry, doctor.
Yeah.
Just now the definition 1.1.2, I think there's a typo there, is it?
Is it? Let me check.
Yeah.
Which one?
Because like they say second line, they say that F is called probability measure on F.
You mean the second line here?
Yeah. In below the definition 1.1.2, the line.
P is
P F and then map to 0,
oh,
1.
okay, yeah. Oh, yeah. All right. Thank you very much. Okay, so remove this further. Yeah, remove this further. So this is something extra. Remove it. Thank you. Yeah. Okay, thank you very much. Yeah. So this is wait. Okay. 1.1.2. Yeah. Thank you. Please remove this F. But that's one that I believe you guys can understand it. So a mapping P from F to 01 is a probability measure if and only it fulfills these three properties. Okay. Well, 1, 2 done. 1, 2 is quite straightforward. Okay, done. Now we just need to verify number 3. Okay. So number 3 is this one. That is. So if we have a sequence of disjoint events, so these two must be equal. Yeah. Okay, so maybe. Okay, let's do it over here. So this is in where? Note 1. Okay. Okay, one by one. I think it's clear. PA greater over 0 for all A in here. So this is obvious. Okay. And also P of omega is equals to 1. So this is directly by 1.2. Okay, we just look at number 3. Okay, number 3 is so we have a disjoint event. So let's say we put it this way. Let's say we have a A1, so which is omega 1, 1 again, and omega 1, 2, omega 1, 3, and so on. And A2 is omega 2, 1, omega 2, 2, omega 2, 3, and so on. And we have a A3 will be omega 3, 1, omega 3, 2, omega 3, 3. So, okay, because everything are discrete, so we can actually label it in a discrete manner like this. Okay, now all these fella disjoint. Okay, so because all AK are disjoint. Okay, so what's the meaning of disjoint? Disjoint means AI intersect AK must be empty set whenever I not equals to K. Okay, so that means all these will not be the same. Okay, so they are not the same. So this one just means that each omega Ki is distinct. Yeah, it cannot be the same. So because, for example, if this and this identical, so that means A intersect B must be the same. So okay, so that's why when they are disjoint, all these omega Ki would not be the same, not identical, each of them. Okay, now we just look at it. So then we can see, because of this, then we can see if we take the unit of all the AK or AM, so that means it's actually we are taking all of them. Omega 1, 1, omega 1, 2, omega 1, 3, and so on. And then we just add in omega 2, 1, omega 2, 2, 2, 3, and so on inside. And also putting 3, 1, 3, 2, 3, 3, and so on. And so on. Okay. So we're going to have a discrete many of them. Okay, now we go back to our definition 3 here. Okay, P of A is equal to this. So we can see this. Okay, so then P of union of all the AK, so that will be, you are summing up all these things, right? So that means it's P of omega 1, 1, and so on, okay? And plus P of omega 2, 1, and so on, and plus P of omega 3, 1, and so on, and so on. So we can group together. Then you can see this one end up to be, you just look at the first line. So the first line is actually just equals to P of A1. Okay. And the second line will be just equals to P of A2 and so on, plus P of A3 and so on. So all this we can, if we use a symbol, so this will be just equals to, we are summating all the pk, k running from 1 to infinity. So then we can see, all right, so we get this relation. So 1, 2, 3, done. Okay, so using this, then we can see that, can make conclusions, hence P is a probability measure. Right, so we cannot simply claim something is event or something is a probability space or is a probability. Okay, so what we need to do is we have to use these two definitions, definition 1.1.1 and 1.1.2, verify for sigma field. We have to verify it fulfill these three criteria. Okay, and then for a probability measure, we have to make sure it fulfills these three criteria. Okay, before we can make a conclusion, this thing is a probability space. Okay. Okay, so that's the reason. Now we have verified this. So that's the reason why I can say that by using this method, we can construct a probability space. This F must be a sigma field. This P must be a probability measure. Okay, so this is okay. So again, these examples have been discussed already, right?
Question. So is the is the CDF of a normal distribution a probability measure?
Come again?
Is the cumulative distribution function of a normal distribution, is that a probability measure?
The cumulative distribution
function, yeah.
Cumulative distribution functions are.
Or okay, is a normal distribution a probability measure?
Okay. Wait. I think I answer your question in the next chapter, right?
Okay.
Okay.
Sure.
Okay. Because of the reason is here. Bear in mind that I mean, in this course, it's a little bit different from the other subjects, right? So in other subject, you might not need to how should I say? You might not need to treat the concept very particular. Okay, this is a math subject in a way. Okay, it's not a stat subject. It's not a applied subject. So that's why in this kind of a theoretical subject, so we have to be very careful with the terms that we are using. Okay, so just now you asked a question like this, something like that. Is the cumulative distribution function for a normal distributions a probability measure? Is this your questions? Something like that?
Yeah.
Okay. Okay, so one by one. One by one. Okay. First of all, we have to see what is a cumulative distribution function. Okay, next we have to look at what is meant by distributions and normal distributions. Okay, one by one first. Okay, since we have started this topic, so maybe. By the way, what is cumulative distribution function? I think cumulative distribution will be just a distribution function. Okay, you have to come back to this again. Huh? Where is my definitions? Okay, here. You can look at here. I think this is not good. I cannot highlight. Okay, this is better. Where's my definitions? Right. First of all, this fella must be a function with domain is f. Now I'll ask you a question. So what is the domain of a cumulative distribution function?
I think it's
What is the domain for cumulative distribution? So if I'm not mistaken, so cumulative, so it's like fxt, right? So which is just you integrating t from -4. So this is the density function, right?
yeah.
Okay. So you look at this thing here. What is your t? So t is any number in between -infinity to +infinity, right?
Yeah.
Okay. So in other words, if you look at here, so that means what is the domain for your fx here? So which is actually negative into infinity. So that means this is a function from R to R. So you look at here, property measure. So the domain must be a sigma field. What is sigma field? Sigma field is, I mean, it's not defined on point, it's defined on set. You get it? Okay. So that means this one is defined. So how should I say?
Doctor, why isn't it a mapping of R to 0 to an interval of 0 and 1? Because isn't CPF just a probability?
Come again. I mean, just I just to let you know, this is a domain and this is a range. Okay.
Okay.
So that means in this case, so you can see, how should I say? So fx in this case, so fx defined here. So anything inside here is an outcome actually. we can say it's an outcome if you're talking about the normal distribution or whatever. So this one is an outcome or just a number. Okay, maybe I will say this is a number. Whatever the thing inside here is a number. Okay, but for probability, when you talk about P, here must be a set. Okay, so this is a set. But I assume you guys know the meaning, the definition of that cumulative distribution function. Yeah, I think you guys know it. You have learned it in your undergrad course. So I think no problem. We can discuss it over here. Okay, so you can see the difference. So for this is a distribution function. So the domains, the object that we assign will be a number. Okay, so but for probability, the object that we want to assign the value will be a set. Okay, an event, a set. So that's why in this case, then you can see that. So this one is not a probability measure.
Okay, what if it was just the density function, not the cumulative?
Which is also not a probability measure, right? Because a density function, the domain for a density function is what they call it, is a number. Okay, so which is also not a density functions. Okay, never mind. Later on, so you can see how to use the density function to define a probability. Okay, and then you can see the difference between this and that. Okay, so at the moment, so just remember the definitions, the three actions here. Okay. Yeah, actually, I'm going to discuss this later, not now. All right, so okay, yeah, good questions. So we come back to your question later. All right. Okay, so I think this is this one done. We have discussed. I think we also discussed this. Okay, maybe we will come to this general sigma field. Okay. Okay. So I think this one I have briefly mentioned it just now. Yeah, for the discrete probability space in section 1.3, we can take F to be P omega, so that all the subset of the sample space are events, and hence can be assigned probabilities. However, this is not viable when the sample space is uncountable infinite set. So again, this one, like you can look at the Reuten books. So only those subsets satisfy 1 to 3 in definition 1.1 are focused. So that's why we only focus on those subsets which fulfill the 3 criterion in definition 1.1.1. Only those subsets we call it as event, right? The reason I mentioned it already just now. Okay. Again, I think I have discussed this already. So this is the example for something to be a sigma field and something which is not a sigma field. Okay. I have also discussed this example. So the smallest sigma field, so-called 301 or power set, is the largest sigma field. And we also have some other kind of a sigma field. Okay. Okay, so we also discussed this, a sigma field generated by a class. Okay, I think we have discussed all this already. We also discussed this very, we call it toy example. Okay. Okay, toy example means it does not has any specific application, but just to demonstrate the idea. Okay. So it's a very interesting examples over here. This is so-called countable sigma field. Okay, again, we have discussed this already. Okay, now let's proceed to this. Oh, where is it? Wow, very far away from here. Okay, I think this is the one. Okay, so come back to this again. Okay. So when omega is R, so it is impossible to design a probability to each subset. So then, when omega is R, we are not allowed to set F to be P omega. So that's why we have to find a another. We have to find another sigma field, which so that we can use it to replace this power set. Okay, so then the best candidate will be the so-called the Borel sigma field. Okay, I think I better use another picture. Okay, so now we come to this general case. Okay, that is. Okay, so we cannot take. Okay, maybe let's put it this way. This is the picture here. when omega equals to r, just now we said, we cannot take f to be this. Okay, so we cannot take this, so we have to find another sigma field. So which one is it? So you can say, in a way, I don't know how, what do you mean by best here? So the best replacement for this is what we so-called the Borel sigma field. Okay, so that's why now it's kind of standard scheme for us when we consider this sample space is R or any interval of R, we're going to consider Borel sigma field. So instead of some other sigma field. So this is kind of the standard replacement. Okay. Okay, now we look at it. What is this Borel sigma field? Okay, so that's the definition over here. So we consider this class of open closed interval in R. So that is all the interval open, excluding the first endpoint and including the first endpoint. So we look at all kind of this open closed interval. Okay, so and then Borel sigma field will be the sigma field which is generated by all this kind of open closed interval. Okay, right now this is a very interesting sigma field here. Then we have to see what kind of subset is a sigma field. Okay, so this is a very first thing that we can see is any interval is Borel set. Borel set means it's an interval, it's an element over here. Okay. So we can see first of all this our definitions here. Borel sigma field is the one generated by this open closed interval. Okay, so all kind of intervals are Borel set. So Borel set means the elements for this. Okay. So we have how many types of the interval? So just look at it. Just to let you know, this Borel sigma field, we use the symbol B, is the one which generated by all the so-called open close interval in the form A, B. So this is what we so-called Borel sigma field. Okay, so we look at here, all kind of interval are Borel set. So we have how many types of the interval? So you can see this. Actually, we have, I also don't know how many types. How many types of interval can we have? First type will be, okay, I just say, how many types of interval can we have? Types of interval. 1 to 4 types, right? Okay, it can be first open close, and secondly, it can also be open. That means we call it open interval like this, and we can have a closed interval. We can also have closed open interval, and anything else. Okay, so we can actually extend this idea to another 4 types. So 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4, let's say 5, which involve infinity. So for example, we can have a closed interval up to negative infinity, or we can also have open interval up to negative infinity. Then we also have this type up to infinity, close one, and finally, I think open. Yeah, I think, yeah, we have altogether 8 types of this interval. Yeah, this can be replaced by any other numbers. I just put 0 and 10 just to demonstrate the ideas for it. Okay. So now, according to our theorems here, any interval is a Borel set. So that means all these are Borel set. So that means from here you can see we can actually have a lot of Borel set here. Any interval will be a Borel set. Okay, so how to do this? So let's I verify some of them with you guys. So the remaining I leave it to you. Okay, so let's do the checking. Check. So okay, case number 1, open close interval must be a Borel set. So this one is true. Okay, the reason is because by the construction. Okay, maybe I'll put it this way. So I can see because B is generated by all open close interval. Okay, so open close interval. So then we don't have to prove anymore. So this is generated by this open close interval. Automatically, all these open close interval must be elements in here. So then we can see it then, hence all open close interval such as the one that I have mentioned here from 0 to 10 are Borel set. So we don't have to prove it. So this is directly from our definitions. Okay. Next. Okay, again, we have to make use of the definitions. So let's look at here. Next, for the second type, open interval. Is an open interval a Borel set? Let's say we look at this open interval 0 to 10. Okay, in fact, you may do it for AB, any value of AB. I just take 0 for 10 to demonstrate the ideas on it. Okay, so next, what happened to open interval? Why an open interval is a Borel set? Or is an event? So maybe we can look at the definitions here. So omega must be an event. So that means in our case R. So A is an event. The complement of A is an event. AN are events for all n. Then the union of all the AN must be an event. Okay. So we're going to use number 3. Okay. This to prove this thing. Okay. Okay. So let's say we look at this one. So example, I just look at it 0 to 10. Why this open interval is an event? Okay, so you may do the verification for all other kind of open interval. So you can see it. 0 to 10 can be written as the union of all these interval. 0 to 10 minus 1 over k. So I think I'm not going to verify for myself. So you guys go and check it out. So you can easily take the union for all this open interval. You can get the the open interval 0 to 10. Okay, now you can see it. So since all these are event. Okay, so this is open close, right? So this is actually based on the constructions here. So all open close are events, right? So all these are event. So by using these properties, so then we can make a conclusion. 0, 10 is also an event. So this is directly by using definitions 1.1.1 part 3. Okay, so the rest, okay, maybe just show you one more. 1, 2, 3. Okay, so maybe okay, this part done, this one done. Okay, maybe okay, so this is easy, so we can look at this one again. Number 5 and 8. Okay, so type 3, 4, 6, and 7. You guys go and do it on yourself. Okay, so we look at 5 and 8. Okay, so look at 5.
Doctor.
Yes.
So no, because you started the explanation by saying that all intervals are Borel sets. So what is it in point number 2? It's Borel set. I mean,
hey, no, I'm not saying, I'm not begin with this. I try to, now I'm actually proving this. I'm trying to explain theorem 1.3.2, why all kind of interval are Borel set. Here
okay.
Borel set second means events.
Okay.
Means
Okay.
events. Okay. So I'm trying to explain why, how to achieve this statement. Okay.
Then I understand that your explanation in number 2 says that you've shown that 0, 10 is an event, but can we then also conclude that 0, 10 is a Borel set?
Which one? Which type? 1, 2, 3, 4, 5, 6, 7, 8.
No, your explanation number 2, the open interval.
Yep.
You've shown that it's an event. Okay, I think we understand that.
Okay.
But have you also shown that it's a Borel set? Or can we conclude that it's a Borel set?
Okay. Sorry, I think I a bit quick. So okay, just slowly. Just slowly. Make it sorry. Okay. Maybe I put it in this way. So when this omega is R, okay, we take F to be the Borel set. Okay, so that means elements of B is a Borel set. Okay, so that means when this, hence we can say that after we have proven this, Borel set means event. When omega is R. Okay. Borel set is an event. So in fact, an element of B is so-called a Borel set. Okay. After we have verified that this, we don't have to verify because of we have said that this B is a sigma field generated by all those open close interval. So that's why automatically it must be a sigma field. Yeah. So elements of script B is a Borel set. So this is a synonym to say that Borel set is an event in this case when omega is R. All right. Yeah.
Doctor, sorry.
Yeah.
Can I ask? Okay, just want to understand what we are doing here, right? Okay, so for example, suppose I take a particular interval 0 to 10, right? So that is a particular Borel set. And then to generate a Borel sigma field, basically then we do the, we generate, it can consist of the empty set, and then the complement of that Borel 0 to 10 interval, and then the entire line, right? That is the entire sigma field, is it?
Okay, so I think I have to do a correction on your statements. First of all, not interval, Borel sigma field is generated by open close interval. Okay, open close. We just look at open close, not all the interval. Okay, we look at first, we define this. So once we have this definition, okay, I think maybe my sequence is wrong. So this one should come after this. Once we have set up this definition, a Borel sigma field is generated by all the open close interval. Okay, then from here we can show that we can verify all kind of intervals are Borel set. You get it? Okay. Not the other way around. We have to begin with this and then we come to this. So maybe have to sort the position for these two things. All right, got it?
Okay.
So this is actually we want to verify for theorem 1.3.2. Okay, we want to verify this based on these definitions here. Okay, so we have actually all the possible interval will be this 8 times. Okay, 1, 2, 3, 4, 5, 6, 7, 8 here. Okay, so the first time we don't have to verify because of the definition open close interval generate this sigma field. Automatically, this must be elements inside here. So that's why the first one we don't have to verify. Okay. However, the remaining we have to verify one by one by using these 3 properties here. In fact, the first 2 or any one of it, these 3 properties. Okay. So the second one I have verified by using property 3, action 3. Okay. Next we can do for others. So I just demonstrate 5 and 8. The remaining you go and do it on yourself. Okay. Get it? Okay. So I would say it's, all the interval like this. So example, negative infinity to, okay, maybe B is an event. Now I think not event. I think better use a Borel set. It's a Borel set because we have. I think it's doesn't matter. So it's an event. Okay. So why? The reason we can write this because we can write this. We can write this as union of negative k to p. So we can get this. And again, this is an open closed interval, right? So again, we have the same. So since this one are event, so not none. Because of this and this one are events. So that's why we can have this statement. This one is an event. So and number 8. Number 8 is this one. Okay, A to infinity is an event. Why? The reason I think we can use this. Okay. We can use these properties to do it. So the reason is because this is equals to the complements of negative infinity to A. Okay, and this one is an event from number 5 that we have shown. Okay, so using this way, we do it step by step. We can also see this is also an event. So you can use 2 and 3 and also the previous result to show that all these kind of interval are events. So we can do it without any issue. Okay, so you do it one by one. So that's why now we can see it. Okay, all kind of intervals, open, close, or close, open, close, close, open, close, open, open, finite, and all these are interval. Borel set. Okay. And next, all singleton, which means a set with only one element, is an event. Okay, why this is an event? Then we can check this. So all singleton, that means set with only one element is event. So for example, we can see is an event. It's a Borel set, maybe same. Okay, you can put it the same idea. So Borel set means event. So this one is a Borel set. Why? Because of how should I do it? Okay, maybe maybe we do it. Okay, so because this is actually equals to the okay, maybe I do it one by one. Do it one by one. So this one, let's look at a proof. Why this is an event? Okay. So the idea is like this. First, we have shown this negative infinity to A and A to this are Borel set. Okay, so because we know this is interval, so from this theorem 1.3.2, so we know this is event. Okay, so this is by theorem 1.3.2. All these are Borel set. These two are Borel set, and so this is also a Borel set. Okay, so why this is a Borel set? The reason again, because of here, the union of two events must be an event. Okay, I think we agree with this. And next, and so this is actually the complement of this fellow. Okay, so first of all, we take two interval. So the union of two interval is a Borel set. Okay, based on these three. And after that, we take the complement for this, then we will get a set with A only. So this one also must be a Borel set. So that's why we also have another interesting picture. So not only interval, on top of that, all the set with only one element must be a Borel set. And also any countable union or intersection of this must be a Borel set. So that means now we can see this, another picture. So then we can see remark part C. Any countable subset of R is a Borel set. Why? Because let's say we can check this. Okay, it's quite easy because let's say if A is A1, A2, A3, A4, and so on, a countable subset of R. Okay, by part B, we know all the AK equals to an element with one AK is a Borel set. Okay, it's a Borel set. Then we come back to this again. If this is Borel set, so then A is equals to the union of all the AK. So it's also a Borel set. So by using property 3. So actually, by using property 2 and property 3, so we can generate a lot of Borel subset here. So then you can see any countable union intersection of certain subset in A, B will be Borel set. So that means actually almost all the subset that you can name will be a Borel set. Okay, only some very weird subset, so that is not a Borel set. Okay, but that is again another story. So that beyond the scope over here. So we are not going to discuss this. Okay, so what I can tell you is, so just give you a remark. So almost all subset of R are Borel set. As long as you can name, so that will be a Borel set. So only those we have to go through a series of very complicated construction. Those are very funny kind of subset. Yeah, that might be not a Borel set. Yeah. So that's why in future you may always assume that all the subset are Borel set. Okay, because those are non-Borel set. Usually you won't see those subset in the rest of your life. Okay. Okay. Now we
So can I say that in a layman's way of saying anything all Borel sets are events, right? So almost all subsets of R are events, right? So things like irrational numbers, for example, are not probably Borel sets.
Yes, you can put it this way. Whatever that in your eyesight are Borel set, you can put it this way. Those non-Borel set will be at the edge of the universe.
Okay, very weird things. Okay.
Yeah, you can put it that way. Yeah, of course, if you were interested, again, you may go and Google it or YouTube. You can see a non-Borel set, a non-measurable subset R. So you can see it go through a series of, you don't know, funny kind of a construction and this intersection, union intersection, and at the end of the day, you don't know what the hell is that. So that is an example of non-Borel set. Okay. As I said, don't worry. I can safely say most of anything under your eyesight are Borel set. Okay, you don't have to worry about the non-Borel subsets. Okay, but just remember, they do have something that is not Borel set, but at the edge of the universe. Okay, you won't see it. Okay, got it. Okay, so as I said, there's a lot of subset that will be a Borel subset. Okay, just now we are talking about this is a case when omega, this is when omega is R, then we, okay, now we look at here. When omega is not R, but a subset of R, we can use this to define Borel sigma field on it. So that is, so that means this, okay. Okay, when omega is just a subset, so what we can do, we can take anything will be B intersect this will be a Borel subset on this subset of it. Okay, so you can look at these examples. Okay, so instead of R, we take our omega to be this one, the open close interval 0, 1. Okay, so then anything, you just take anything which intersect any Borel subset of R intersect with this omega will be a Borel set. Okay, so I think this is quite straightforward. You can just check it on yourself. As long as you take any B belongs to BR, so this will be Borel subset for this restriction on it. Okay, next we try to discuss how to construct properties on R. So we look at here. Again, I'm not going to go into the detail, the properties for Lebesgue measure. Just let you know how to define it. Okay, so this Lebesgue measure, in a sense, you can set it Lebesgue measure of an interval is just equals to the length of that interval. Okay, you may put it this way. Lebesgue measure of an interval will be the length of that interval. Okay, so that will be this one. So that means, let's say the Lebesgue interval for this interval, the Lebesgue measure for this interval, AB, so that will be B minus A. Okay, so let's say what happens if we consider a non-interval. So if AK are disjoint interval here, disjoint Lebesgue Borel set, so we can just simply say the Lebesgue measure for it will be the summing of this thing. So from here you can see this is actually similar to that in here. Okay, maybe I just write down here first. Okay. So for any interval L of this, we define B minus A. So then we look at it. Number 2, when AK belongs to our Borel subset, okay. So we just define, and then disjoint, okay. The unit of all the AK will be equal to the summation of L of AK. So this is the case over here. So if you compare this with our definition of probability, well, you can see it, they look the same, right? Because if you look at this, so for sure, if fulfilled, it must be positive. And you can compare this with this. So they are the same. So what's the difference between Lebesgue measure and the probability? The only difference will be here. Okay. So for probability measure, P of omega is 1. However, for Lebesgue measure is what? What is this? L of omega. So let's say if you look at here, omega is R. So L of omega will be L of R. So that means L of negative infinity to infinity. So what is the value? So this is actually negative infinity. So this is infinity. So that's why, because of this, so this is not equals to 1. So that's why from here you can see a Lebesgue measure is not a probability measure. Okay. Anyway, this is why we call it measure instead of probability measure. Okay, let's look at a very simple, not simple, one example to describe a probability space for this non-countable one. Okay, so this is an example 1.3.6. So this is a uncountable case sample space. Okay, so the question is the formulation is quite straightforward. Okay, so let's say we have let's say we have just 2 points. So the distance here is 20. Okay, so A and B. And supposing we just simply pick a point in between these 2 points. Okay, so let's say we pick any point here. So we just simply take omega. What is meant by omega? Omega will be the distance we measure from point A to here. Okay. So here we can just simply take an outcome is the distance of this point C to A. Okay. So from this setting, so you can see that this omega, it must be a point in between A to B, and point C must be a point in between A to B, and omega is the distance. I think I shouldn't put this way. Maybe I should put this as a. We do the setting. Omega is the distance between A to C. I think that's a clear picture. So we just simply pick a point, C, and then we see where's the distance of C to A. So from here, I think it's clear. The range for omega will be from 0 to 20, right? So because C could be A or B, depends on how we want to put the position. So in this case, then we can see our omega, the sample space will be the closed interval 20 to 0. Okay, so this is because of our omega, small omega will be 0 to 20. We wouldn't consider the thing out of the range here. So then you can see this one, omega is uncountable. Okay, or this is a subset of R. So in this case, then we can take our F to be B omega. So the Borel sigma field on this closed interval 0 to 20. Okay, so how to define the probability measure? Then what we can do is we can define P of this interval there may be so we can take any P of sub-interval, so to be the length of the sub-interval so divided by the total length. So the total length must be 20. So that's why that is equals to divided by 20. Okay, so this is how we set this thing. So this is an example. So example, if we take the interval from 2 to 9, so the probability will be 9 minus 2 over 20. So that will be 7 over 20. Okay, so this is how we can set define this probability space on it. So I think this is based on the experiment. Next, we always take the Borel sigma field to be the Borel sigma field. Next, we use this way to construct the probability on it. Okay, this is the case. Then you can see this is an example of what we so-called a uniform distributions. Okay, so now we come to, I think this is the most important one, these propositions 1.3.1. Okay, in fact, this is the criterion for us to verify whether how to say it? A formulation is a probability space. Okay, it's a formulation. So we look at here. Okay, supposing omega is R, then in this case we always take the sigma field to be the Borel sigma field. Okay, and again, first of all, if we have a function f is greater than 0 and satisfy this, then this P must be a probability measure. Okay, so this one gives us a criterion to check whether a P in R is a probability measure or not. So this is a very important one. So that means I better write down here. Okay, so this is give us a criterion for P to be a probability measure on R. Okay, so how is it? First, this is the one. The setting will be omega is R. Okay, and then we take script F to be the Borel sigma field. Okay, so this is already fixed. Always take whenever interval of R or R, we always take Borel sigma field. Okay, next, we just need to verify this. First, we have to make sure F is a positive function, small f. Must be positive, okay? And secondly, when we integrate from negative infinity for this F, value is 1. Okay, so when 1 into this, okay, so in this case, then if 1, 2 is true, then this 3, this P defined as AB is equals to, we integrate from A to B, F is a probability. Right, so the criteria is quite straightforward. First of all, we have to make sure this small f is positive. And after that, if we integrate this f must be integrable. And after that, we do the integrations. It returns value 1. Once it's fulfilled these two criteria, then this P defined in this way must be a probability measure. So when you look at here, I think you know this thing. So this is actually the density functions for the distributions. Okay. Okay, so in this proposition 1.3.1, so the probability measure is so-called, we call it an absolute continuous. Okay, forget about this one, doesn't matter. So in this, so we use usually we use a Riemann integral most of the time. Okay. So maybe you look at this example. Okay, so determine each of the function below, define a probability measure on here. So ABC. Okay, so which one can define a probability measure? A, yes or no? So since actually it's not difficult, like I said, you just need to verify 1 and 2 here. Okay, so I can give you the answer. This is no. This is yes. This is no. So what is the reason? So what is the reason? What are the reasons? No, yes, no. Okay. Actually, you just need to verify these two criteria. Okay, the first one is no, because our answer is here. No, because F is not non-negative. Because you can look at here. Fx is x negative square root of 2 to 2 here. So you can take f of minus 0.9 negative. So this is negative. So it violates these properties. So that's why the answer is no. Huh? Okay. B. So you can easily verify. First of all, f is always greater than or equal to 0. I think 1/20. Next, you do the integrations. So 0 to 20. So that will be 1. Okay. 1 and 2 pass. So this is fine. So how about C? So we can easily verify this.
Normal.
Not normal. Looks
Scale.
like normal, but it's not normal.
Scale. Is it scale normal?
No, it's okay. You look at here. Please check. What is the? So the density function for normal is like this, right? It have to be square root of 1 over 2 pi sigma. Okay. So yeah, this is normal. However, now we don't have this. Okay.
Yeah.
Okay. That's the issue here. So that's why now you can see it. So you can verify the reason if you integrate from negative into infinity for f. So that is we integrate this. So we are not going to verify. So the reason why I want to put a factor here, because if without that factor, we'll give you the value square root of 2 pi. Okay. So this is not equals to 1. Okay. So, and this is not equals to 1. So hence you can say that hence it does not produce a probability measure. Okay. So actually, there are only 2 criterion that you need to check. Okay. First of all, make sure f is a non-negative functions. Okay. Secondly, when you do the integrations of f over all the domain, so it must be 1. So once you fulfill these 2 criterion, then you can just simply define your p to be this. So this is a probability measure. Okay, so I go back to, remember, just now you asked, someone asked me a question about the cumulative functions. So you see, this is how we define a probability. So it must be in interval. Okay, whereas cumulative function, you define on a particular value only. So that's the difference between a cumulative function and the distribution function and probability. But they are related. Okay. Yeah. So there are simple oh, wow. Okay, so I think I better stop here now. Now, time's flying. It's already 9:24. Okay, so 5 more minutes. So I think I better stop here. Any other questions? Any other questions? Okay, just one more time. Okay. Okay, so just one more time. So this thing, how do we know when we talk about the sample space is uncountable set? So usually will be a subset of R or R. Okay, so how to construct the probability space? Okay, first of all, we can take F to be BR. We always do that. Okay, so this is the best alternative for power set. Okay, next, how to construct the probability space? So we just construct one F. And then this one, the positive small f, and the integer value will be 0 to 1. So once we have an f satisfy this property, so this is what we so-called density functions. I think you guys are aware of that. So once we have a density function, we just construct our p to be this way. That must be a probability measure. I don't want to verify it. Okay, so just accept it. So this is for the case when our omega is R. Okay. What happened? The first 2 cases are thing just again. We have a standard scheme. Okay. Just go back to it. We have a standard scheme. When we have I think a direct goal to come to this the uncountable one. Oh, sorry, discrete one. Okay. So when we have a discrete case, So we always take F to be a power set. Okay. Next, we just need to construct a sequence of function, a sequence which satisfies these two properties. So you can see these two are more or less the same. Okay. You can say the summation will be integrations. Just replace the summation with the integration. Yeah. So then we just define it. This will be equal. Okay. So just like that, discrete and uncountable case. Right. Okay. I think I better stop here now. Okay. So have a nice weekend. So see you next week.